is Statistical Rethinking, second edition, chapter 15. We're in the medium difficult questions, and this is 15M4. So here, if you're going to use the Colab sheet, just make sure that if you go to runtime, change runtime type, that you're in R here. But we're not going to use the rethinking package here. You certainly could, but I'm just going to use the inbuilt functions of R, namely LM here, because we can make the point just as well without having to take a bunch of time to run these models. Okay, so we're going to simulate data from a DAG that looks like this. Okay, X causes Y causes Z. And then we're going to fit a model that predicts Y, this kind of mediator variable here, using both X and Z. And what we're going to find is that the results don't really match our data generating process, and so we're meant to discuss the confound that arises here. Okay, at least in terms of the causal influence of X on Y. All right. So like I mentioned, we don't need the Bayesian framework here to make this point, and so I'm not going to use that. I'm just going to use base R. So first I need to simulate some data. So I'm going to have 100 observations, and I'm just having X be a normal random variable with mean 0 and standard deviation 1. That's what you get when you just have R norm and then put how many samples you want. And then I'm going to define this coefficient, that you can imagine sitting on top of the arrow between X and Y, and I'm just arbitrarily picking 1.5. You can pick whatever you want. And then I'm defining Y in terms of X, so I'm saying that Y is A times X, and then I'm adding some random noise here. And then I have that Z is, and then I'm defining another coefficient, B, again, arbitrary value. You can pick whatever you want. And then Z, I'm saying is B times Y plus, again, some random noise. Okay, so now I'm going to run the regression. If you're, hopefully you're familiar with this in R, but I can just run normal linear regression using the LM function, Y, this little tilde sign, X plus Z. Okay, and then I run my summary output. Okay, so I've ran this. And then the summary will give me the values of the coefficients. Okay, so this is what it looks like. So now if our regression model were causally valid, okay, then the coefficient here for X, that value right there, should approximately be 1.5, right, which again was the causal effect of X on Y. And we see that that's not the case. All right. Okay, so we should have guessed that was the case, right? Because, our regression is regressing Y on X as well as Z, but Z, is not a cause of Y. In fact, it's an effect of Y. It's a descendant of Y, okay? And so we should have guessed that the coefficient that we got for X, and Z for that matter, although it's, if we were to flip some arrows around or something, but we should have predicted that this would not equal the value that we encoded for A here. Okay, we should already have guessed that, okay, simply because our regression is not reflecting, the causal genesis of the data. But in this particular case, what's happening? There's something interesting happening here, which is when we condition on Z, we are conditioning on a descendant of Y. Okay, and so earlier in the book this was discussed, but what happens when you condition on a descendant? Okay, well, it's kind of like conditioning on the parent of that descendant. Well, here, what is the parent of Z? Well, it's Y. And so in a weird way, when we have this regression, we are kind of conditioning on the outcome itself, okay, insofar as Z is a descendant of Y, all right, and Y is causing Z, all right. So that's weird. We probably don't want to do that. It just feels weird. Now, so we're meant to discuss what kind of confound. So I mean that's in terms of inferring causal inference of X on Y. and that's the confound. But it also strikes me that okay, so here we've done, we've done this, we've conditioned on the outcome statistically. But if we were to do this in the course of an experiment, right, or observational study, um, where we are conditioning on certain values of y, we would have called that selection bias. Okay, and so it strikes me that what we've done here is something like a statistical version of selection bias. I mean, not exactly, but by conditioning on y, we are conditioned on particular values of y, and therefore we have some kind of selection bias or something like that. I don't know if what we've done here actually has a name. I've certainly never heard of one, but anyway, we'll call that good.